Okay, Chapter 3, EKG, Basic Electrophysiology. We're going to talk about a lot of things. You see myocardial cell groups and the functions and 4 primaries of cardiac cells, the major electrolytes, the movement of ions, cardiac D and repolarization, the refractory period. We're going to talk about a lot of stuff. So let's get going. Let's start with some basic cell groups. So let's take a closer look at myocardial working cells and what they do. So myocardial working cells are the ones that handle the actual physical contractions of the heart. Now these contractions are what allow the heart to pump blood throughout the body, which is pretty essential for everything to keep working smoothly. Now these cells make up the thin muscle layer in the atria, allowing the atria to contract effectively. But in the ventricles, they form a much thicker muscle layer. So that's key for creating the strong contractions that's needed to pump blood into the arteries and then just keep that whole circulation going. So the main job, let's talk about some primary functions here. Main job of the myocardial working cells is to contract and relax. Now these actions are what physically make the heart pump blood, which is essential for keeping everything in your body functioning properly. So when these myocardial cells contract, they create pressure that pushes blood through the cardiovascular system. Now this is vital for maintaining circulation, helping oxygen and nutrients get to the tissues that need them. So without these contractions, blood wouldn't flow the way that it should and your body wouldn't get the fuel that it needs to stay healthy. We're still talking about these cell groups. So let's take a little closer look at what makes pacemaker cells so unique. So we're going to talk about specialized pacemaker cells. So unlike other heart cells, these specialized pacemaker cells, they don't contract. So that's non-contractile cells. Their main job isn't to pump blood. Instead, they manage the heart's electrical signals, which are essential for keeping everything running smoothly. Now these cells are crucial for controlling the heart's rate and rhythm. They do this by coordinating regular depolarization, making sure that the heart beats in a steady and organized way. Now the location in the heart, these pacemaker cells are located in the heart's electrical conduction system. So it includes important areas like the SA node or the sinoatrial node, the AV node, the atrioventricular node. Both those play key roles in starting and regulating the heartbeat. So you see here, we're going to talk about the specialized pacemaker cells and the primary function. So the main job of these, generate, conduct electrical impulses, crucial because they set the heart's rhythm, essentially telling it when to beat and helping keep everything in sync. Now it does have some autonomous activity because what's really fascinating about these pacemaker cells is their ability to create electrical impulses all on their own. They don't need help from any nerves or anything of that fashion. So this autonomous activity, it ensures that the heart maintains a steady rhythm even if there's no external signal telling it to do so. It's what keeps the heart beating reliably day after day. So how does the cardiac cells respond to stimuli? So we'll talk about threshold. So the threshold is that critical point at which a stimulus becomes strong enough to trigger a response in the cardiac cells. So you can think of it like a tipping point. Once that threshold is hit, the cells are primed to take action. Now here's kind of a weird part. Once the threshold is reached, all the cardiac cells respond to the stimulus. It's not a maybe or a some response, it's an all or nothing deal. So it's an all or none phenomenon. So if the stimulus doesn't reach that threshold, none of the cells will respond. So this helps ensure that the heart's contractions are consistent and well coordinated, keeping everything in sync for effective pumping. So let's talk about the 4 characteristics that make cardiac cells unique. So we have contractility, so that's a mechanical function. So contractility, also called rhythmicity, that refers to the heart's ability to shorten and contract in response to an electrical signal. Now when the right stimulus hits these cells, they tighten up, which is essential for pumping blood throughout your body. Now this rhythmic contraction is what keeps your heart beating steady. And then we have automaticity, so that's an electrical function. So automaticity is a fascinating feature of cardiac pacemaker cells. These cells can spontaneously generate electrical impulses all on their own without needing any external stimulation. That means that even if no outside signals are coming in, the heart can still produce its own rhythm, ensuring it keeps beating continuously and consistently. Now let's take a look at the last two. So we got excitability, which is an electrical function. So excitability, sometimes called irritability, is the ability of cardiac cells to respond to electrical stimuli. So when these cells receive an electric signal, they wake up and they get ready to contract. So this feature is essential for the heart to react to signals that prompt it to beat. And our last one, we have conductivity, and that's an electrical function. So conductivity, that's about how well cardiac cells communicate with one another. So when one cell gets an electrical stimulus, it passes that signal along to neighboring cells. So this ensures that the heart works as a unified whole, so all parts of the heart contract together in a well-coordinated manner. So this table just shows you all four of the characteristics we talked about, where they're located at, and then what function that we see. So we see automaticity in the SA node, the AV junction, the Purkinje network fibers, solubility. There's no reason to just walk you through this. You're able to look at that and figure it out. So let's talk about some electrolytes and how they impact the heart's function. So first, what are electrolytes? Well, they're substances that dissolve in water to create charged ions. Now, when these compounds break apart, they form positively charged ions called cations and negatively charged ions called anions. Now, they have some importance for myocardial cells. So myocardial cells are surrounded by electrolyte solutions, which are essential for their function. And the balance between cations and anions help maintain the electrical environment needed for heart contractions to happen properly. And the way this works is these electrolyte solutions allow charged ions to move in and out of the cells. So this movement is crucial for generating the electrical signals that trigger the heart to beat. Some of the key ions that we'll talk about, we see potassium and sodium, calcium, magnesium, are some of the key ones for heart health. Each of these plays a pretty specific role in ensuring that the heart can function smoothly and then maintain a steady rhythm as well. So let's talk about potassium and sodium in our heartbeats. So potassium plays a big role in both depolarization and repolarization of cardiac cells. Now, during depolarization, potassium helps prepare the heart muscle to contract. Then in repolarization, potassium ions move out of the cells, helping reset the electrical state of the heart. So this back and forth action is crucial for keeping the heartbeat steady and coordinated. And then sodium, it's just as important, especially during depolarization of the myocardium. When the heart's stimulated, sodium floods into the cells, creating a positive charge inside. And then this sudden influx of sodium, it triggers the heart muscle to contract, which is essential for pumping blood throughout the body. We'll talk about calcium. So when it comes to cardiac function, it's pretty important. It plays a key role in both depolarization and myocardial contraction. So when calcium floods into the cardiac cells, it triggers the muscle contractions that make your heart pump blood. And then we talk about magnesium. So it may not get as much attention as some of the others, but just as important. It helps regulate processes in the heart, including the activity of other ions like calcium, and it's essential for keeping a healthy heart rhythm. And then phosphorus, that's an anion. It supports energy production within the heart cell. So it's part of the ATP, which is the cell's energy currency, providing the fuel needed for various cellular functions, including heart contractions. And the last one we'll talk about is chloride. That's another anion that plays a role in maintaining the electrical balance of cells. It helps regulate the fluid balance in the heart, contributing to the overall stability of the heart's electrical environment. All right, so now we see we're going to talk about some movement of ions. So let's chat about the important ionic differences in cardiac cells and how the sodium-potassium exchange pump, how it keeps everything in balance. So inside the cardiac cell, there's a high concentration of potassium ions. Now, this makes the inside of the cell negatively charged compared to the outside. That creates just this cozy negative environment that's ready to jump into action whenever it's needed. Now, on the other hand, sodium ions are more concentrated outside the cell. So that helps create the positive charge on the outside, which is key for triggering heart contractions when it's time to pump blood. Now, the sodium-potassium exchange pump that I mentioned, this is where things get a little bit more interesting. So the sodium-potassium exchange pump, it acts kind of like a busy doorman. So it actively moves sodium out of the cell and it brings potassium back in. So this process is going to be vital for keeping the right balance of ions inside and outside the cell. Now, you might think, why does any of this matter? Well, by regulating these ion concentrations, the pump ensures that the cardiac cells are always ready to respond to electric signals. So this balance is crucial for the heart's ability to beat in a coordinated way, and that just keeps your heart functioning smoothly. So we're still talking about movement of ions, and let's talk about the ionic differences. So across a cell membrane, so the polarized state refers to the resting condition of a cardiac cell. And there's a distinct electrical charge difference between the inside and the outside of the cell. So inside the cell, the environment is electrically negative, and while the outside is positively charged. This difference in charge is essential for the cell's ability to function properly. Now, the negative charge inside the cell is mainly due to a higher concentration of potassium ions and negatively charged proteins. On the outside of the cell, sodium ions are more concentrated, contributing to the positive charge. So this ionic difference, pretty crucial for maintaining the resting membrane potential, which prepares the cardiac cell for future electrical activity and contractions, and that just helps the heart beat efficiently whenever it's needed. So depolarization, let's dive into some cardiac depolarization, key part of how your heart beats. So what happens is when an electrical impulse spreads throughout the myocardium, it causes significant changes in the heart muscle fiber. So that phase is called depolarization. During depolarization, sodium ions, they rush into the cardiac cells. So this influx of positive ions flips the cell's interior charge from negatives to positives, setting off an electrical shift. Now, how it works is the rapid entry of sodium ions that triggers the electrical signal that leads to muscle contraction. It's like flipping a switch that activates the heart muscle to start contracting. So why does it matter? Well, cardiac depolarization is crucial for starting the heart's contraction. Without it, the heart wouldn't be able to pump blood effectively, throwing off circulation and putting the body at risk. Now let's talk about some repolarization. So that's a pretty essential phase in the heart's electrical cycle. So what happens is after an electrical impulse spreads throughout the myocardium and causes a contraction, the heart needs to rest. So that process is called repolarization. So during repolarization, sodium ions that rushed into the cell during the action potential are pumped back out. At the same time, potassium ions move back inside the cell. So the movement of those ions, that helps restore the original polarized state of cardiac cells, making the inside of the cell negative again relative to the outside. It's like resetting the system for the next action. So cardiac repolarization is key to preparing that heart muscle for the next contraction. It ensures that those cells are ready to respond to the next electrical impulse, helping maintain a steady, coordinated heart rhythm. So that kind of just everything we've been talking about. We see polarization, we see sodium and potassium, we start seeing some movement and depolarization, and then repolarization, we see them flip back. Now, just a few terms. Basically, this is just me just reading some of this to you. But let's break down the resting membrane potential of your heart cells. Pretty important to understand how all this works. So the resting membrane potential, basically the state of a cardiac cell when it's not doing anything. It's just chilling. It's like it's the off switch before the cell gets activated. So in this resting state, the inside of the cell is negative and the outside is positive. So this difference in charge is what sets the stage for everything to function properly. So the negative charge inside the cell comes from a higher concentration of potassium ions and other negative components. Now, meanwhile, outside the cell, you've got more sodium ions, which helps create that positive charge. Now, keeping this resting charge is super important. It means the heart cells are ready to respond quickly to signals and jump into an action when needed. So it just keeps everything in sync. Now, action potential. So it's the energy signal that kind of makes your heart beat. So action potential, that change in the charge across the cell membrane of the heart cells. So think of it as a signal that tells the heart muscle to contract. So when a stimulus comes in, sodium ions flood into the cell, which makes the inside of the cell temporarily positive. This quick change in the charge is what triggers the heart to contract. So this change in charge makes the heart muscle contract. It's like hitting a switch that makes all the cells work together to pump blood. Now, without that action potential, your heart wouldn't be able to contract properly and pump blood. So it's absolutely essential for keeping blood flowing throughout your body. Now, syncytium. So let's talk about that for a second. So it's a group of cardiac muscle cells that are all connected and they work as one big unit, not individual players, just a big team. So these heart cells are linked to the structures called intercalculated discs, which contain these gap junctions. Now, these gap junctions act like little shortcuts, allowing electrical signals to travel super fast between the cells. So this helps the heart beat in sync, so every part of it contracts together smoothly. Now, this teamwork is going to be essential for the heart to function properly. It ensures that all the heart cells work in harmony, making sure that the heart beats in a coordinated fashion. So it's like a well-tuned orchestra where every player hits those notes just at the right time. Now let's move on to permeability. So another important concept for how the heart works. So permeability is about how flexible the cell membrane is. So it determines how easily ions, and what we've been talking about, so like sodium, potassium, calcium, how they can move in and out of the cell. So this is key for things like sending electrical signals, maintaining the right balance of ions. So the way it works, the cell membrane can adjust its permeability to let certain ions in or out at just the right time. So this control is vital for creating action potentials and triggering muscle contractions. So changes in permeability, that helps the heart respond to stimuli and control its electrical activity. So that's how the heart maintains a steady rhythm and beats effectively. And then we go to polarized state. So we're getting there, so hang with me. Let's talk about the polarized state. And of course, we're talking about cardiac cells, so it's pretty essential for how this heart functions when we talk about this polarized state. So the polarized state is like a resting phase for the heart cell. In this state, the inside of the cell is electrically negative compared to the outside. So kind of like the cell is charged and ready to go. This difference in charge is crucial for the cell to react when it's time for the heart to beat. So the negative charge inside the cell comes from a higher concentration of potassium ions and negatively charged proteins. On the outside of the cell, there are more sodium ions creating a positive charge. Now this balance of ions sets up the electrical potential, getting the cell ready to react when needed. And you might think, well, why does this matter? Well, this polarized state is vital for maintaining the resting membrane potential. It keeps the cardiac cells in a kind of a standby mode, so ensuring they're ready to respond to electrical signals. So that's, of course, key for smooth and coordinated heart contraction when the heart needs to beat. All right, we got out of those. So refractory periods, let's kind of take a look at those. Pretty important to keep everything working right. So what are refractory periods, you might ask? Well, that's a good question. Refractory periods are the times when the heart muscle takes a little break. So during this time, the heart can't respond to another electrical impulse right away. It's like the muscle needs to relax and reset before it can work again. Now, for the atrial muscle, this relaxation period lasts about 15/100ths of a second. For the ventricular muscle, it takes a bit longer, around 0.25 or 0.3 seconds. So refractory periods are essential to avoid the heart contracting too quickly. Without them, the heart could end up having chaotic beats or even fail to pump properly. It ensures the heart can take its time to reset, keeping everything in sync and then allowing the heart to pump effectively. And then we have an absolute refractory period. So it's a key part of how the heart keeps everything running smoothly. Now, kind of a quick definition, we say the absolute refractory period is a phase during which a cardiac cell cannot respond to any new electrical stimulus, no matter how strong the signal is. So the cell just won't activate during this time. It's like the heart is taking a little mandatory break to make sure that it doesn't get overloaded. Now, during this period, the cardiac cell cannot spontaneously depolarize, which is the process of preparing to contract. This is really important because it gives the heart muscle a chance to recover after each contraction. So without this recovery phase, the heart could get confused and end up with overlapping or chaotic electrical impulses. That throws off the rhythm and it leads to potential problems. And then we have the relative refractory period. So the relative refractory period comes right after the absolute refractory period. Now, during this phase, the cardiac cell's almost fully repolarized and getting ready to respond to another signal. So there is some potential for stimulation. So during the relative refractory period, the cell can be triggered to contract again, but only if the incoming electrical stimulus is stronger than usual. So while that cell is recovering and getting ready for the next impulse, it's not completely off limits. It just needs a little extra push to fire. So this allows the heart to respond to signals, but it still ensures it's not jumping the gun too early. And that's it. I know this has been really exciting. However, we'll move on to the next one. Talk to you next time.